Hi and welcome to this month's EMBL ABR webinar, which will be about Nextflow and its features of scalable, shareable, reproducible computational workflows across clouds and clusters. My name is Christina Hall. I'm from Melbourne Bioinformatics, which is a node of EMBL ABR, and I'm your host for today. My colleague Susanna Bacon from ARDC is behind the scenes co-hosting for us. EMBL ABR is a distributed national research infrastructure network providing bioinformatics support to life science researchers in Australia. It's been set up as a collaboration with EMBL EBI to maximise Australia's bioinformatics capability. There's currently 13 nodes across Australia, each of which undertake or support bioinformatics research around several key areas. They are data, tools, compute, training, standards, and platforms. Before continuing, I'd like to mention a few housekeeping items. We'll mute all attendee microphones during the presentation to minimise background noise. And if you have a question, please type it into the question box. We'll look at the questions at the end of the presentation and relay them to our speaker. The broadcast will be recorded and made available on the EMBL ABR YouTube channel, and we'll notify you by email when that happens. Today, we're very happy to have Radoslav Suchecki speaking to us. Brad, over 10 years experience, has gained plenty of experience in the field of bioinformatics with expertise in scientific software and pipeline development, genomics, transcriptomics, phylogenetics, and as well as high performance and cloud computing. Brad studied computing sciences at the University of East Anglia in Norwich, and he completed his PhD there too on algorithms and distance measures for phylogenetic networks and multi-labelled trees. For his postdoc, he moved to the University of Adelaide, where he developed software tools and analysis pipelines for genomics and transcriptomics of breadwheat. He's now a research scientist in CSIRO's crop bioinformatics and data science team, where he develops tools and practices that facilitate reproducibility, reusability and scalability of analytical workflows. In today's webinar, we'll explore the key features of Nextflow, the reactive workflow framework and domain-specific programming language, which follows the data flow paradigm. To look at how Nextflow can be used to develop, execute and share pipelines, we'll step through developing shareable version-controlled, container-backed workflows, which can be executed across different environments. Okay, so over to Brad.
Thank you, Christina, and thank you, Susanna, and thanks to EMBL ABR for organizing this. As indicated, today we'll focus on Nextflow and how it can be used to generalize our pipeline and workflows to run on both on local HPC and cloud compute. So the challenge we're talking about here is that large analysis workflows are really fragile ecosystems of software tools, scripts, and dependencies. Now, this makes them not only reproducible, but sometimes it's hard even to rerun tasks or run them outside their original development environment. This even affects smaller workflows, and this is the challenge we want to address. There are a multitude of reasons for that, and first and foremost, probably, is being able to rerun your own analysis or rerun them on new data, be able to rerun, extend pipelines, given updates to software, new versions, error found in code or results. You may come up with new ideas and test them quickly without re-implementing a lot of code. You might also need to switch to a different compute environment, perhaps because your local server or cluster is not able to scale to the needs of your new data. Now, to do all that, we have a long list of things that are needed for that to happen reliably. And some of those, perhaps the most important ones, include version control, because you want to be really specific about what code you have used to generate. We have used to generate specific results. Obviously, it's also relevant to the development process itself. We want to also capture the software environment, and possibly, or one of the best ways of doing that at the moment is to have that capture in containers. And also, it would be really good to be able to run our workflows across different compute environments. Finally, we want to be able to share our tools and workflows with others, whether in our teams or with broader community. We have looked at a number of workflow management systems, and Nextflow has drawn my attention for various reasons. Well, Nextflow is a reactive workflow framework and a domain-specific language. It arose in the field of bioinformatics, so there are quite a few features that are bioinformatics specific, although the system itself is much more general than that. So it's got a lot of syntactic sugar that will help with bioinformatics tasks. There are certain design solutions which improve the experience for a bioinformatician developing pipelines, but it is definitely more general than that. You can apply Nextflow way beyond bioinformatics. It's designed for scalability and using existing scripts. The parallelization is implicit. If your data breaks down nicely into separate chunks, perhaps there are different samples that you must process, then this should happen sort of for free if you design the pipeline correctly. And the separation of pipeline logic from the definitions of software and compute environment allows this flexibility of running it across different systems, and also helps the shareability. So you can have others using your workflows without spending hours, days, or perhaps weeks trying to set up the right environment. So Nextflow comes with quite a few really neat features. So support for different execution environments comes out of the box. For example, whether you're using a Slurm cluster or Amazon Cloud Services or any of the other systems listed here. Also, the support for Docker and Singularity containers is quite advanced, with automated mounting of binding of directories that with the data you want to process and where you want to store the results. It's also linked to provide link to Git repositories or Git registries and integrated with them really well, which I hope we'll be able to illustrate in one of the next slides. Now, the main building blocks of an Nextflow script are processes. So a process is a definition of how a given task will be executed, what are the inputs and the outputs. So you define a process, and this can be run multiple times for different input chunks, which then each individual instance of that process you would call a task. Each task is executed in its own directory, which helps with safe and block-free parallelization. It helps with easy cleanup, and it facilitates the caching system so that the tasks can be rerun only if either the inputs or the script's definitions changed, so that you don't have to recompute the whole workflow from scratch just because something failed way downstream. And in addition to the processes, we've got channels connecting those processes. So channels conceptually are basically those pipes through which data flows into the processes and between processes. In addition to channels, you've got a suite of operators which you use to shape the data flowing through those channels, combining, merging, splitting, and various other operations which will allow you to shape the data such that it's processed then by the processes in the way that you intend. So I mentioned the parallelization for free, and this is linked to how channels and processes work. And this diagram gives you an idea. So you've got a number of data sets or data chunks. This could be separate samples, perhaps, that you want to process, and those are those flow through the channel, and then a process which defines this channel as its input spawns that many tasks, each processing that each chunk separately. Further down, you would have more processes, more channels connecting them, and you could either keep on splitting or merging the channels as needed, as long as given data chunks can be processed separately. This then sort of just happens, which is one of the beauties of Nextflow, that you don't have to worry about the separate the process happening separately here. So if you have enough compute power, whether on a cluster or a big server or in the cloud, so in the cloud, I guess that translates basically into simple dollar cost. This happens, and the upside is that as opposed to more of a basic pipeline setup where you just submit individual jobs or one big job with multiple tasks, you should get a reduce the overallocation of resources. So you could have one big task that consumes a lot of memory or a lot of CPUs, a lot of time. Other tasks which are not dependent on it can run at the same time, or that you don't have to over-allocate resources for those, basically. Now, how do we get started with Nextflow? You'll need essentially a Linux system. I haven't tried any of the alternatives for that purpose. You need Bash and you need Java. Everything else is packaged with the binary, and the install is trivial, as you can see here. In addition to that, if you're developing a pipeline that relies on specific scripts or specific tools, you obviously need those tools available in some way. And there's a number of ways in which those can be made available, from the simplest, your binaries being available on path or under bin direct subdirectory of your Nextflow workflow. And as mentioned before, thanks to this integration with different systems, this can also be Docker or Singularity containers, Conda environment definitions, or on your HPC cluster, you might opt for using the HPC module system that you might have available. So let's get started with Hello World example. This is taken from the official Nextflow repository directly here. Your first Nextflow script can start with the shebang line. This is optional. If you don't want to execute it directly, that's not strictly necessary. Here we say that echo true to ensure that the outputs of the script block or any script block, if there are more, are printed to the terminal directly. Otherwise, in big workflows, you wouldn't use that because you wouldn't want all your standard outputs printed to the screen. In this case, that's intended. So echo true to see the printouts, and then we define our first channel. So this is the name of the channel. You can call it whatever you like. So here it's called cheers, and it takes a list of different greetings, different strings, and generate a channel which emits one of those strings at a time. Then we have a process definition, which defines we have an input block where we say that a value X taken from the channel cheers is the input. So what will happen is that this process will be executed as many times as we have inputs in the channel feeding that process. Then for each of those, tasks, the script executed we have just a simple bash script here. This will just print this this string. So when we actually run it with the command nextflow run hello, because that we haven't yet written it locally and we don't have a script called hello, Nextflow will look up GitHub repositories, and again, if Nextflow is linked to your own repository, then it would look in your GitHub repository first. If it doesn't find hello there, it goes to Nextflow.io. It pulls the script that we just saw from there and executes it. So what we get is that each of the process is executed for each of the inputs. So we've got that many tasks, 4 different tasks. Each is saying our hello world, and that's it. And you might notice the little hashes that are generated here. We'll come back to those in a moment, but it is quite useful then for debugging and seeing how things are done under the hood. So, as I mentioned, the script is pulled from the repository. If we run nextflow info hello, you'll get details of where it has been pulled from, where it has been saved locally, what's the actual script name, because hello was just the repository name. And you also get the list of revisions available. That's one of the functionalities of Nextflow, which really helps with sharing pipelines, and this is a part of its integration with version control, with Git version control. So when you want to run a script, we've already saw the Nextflow run hello, but you could be more explicit here. It could be Nextflow run and the full repository name, the organization or username plus the repository name. And then you could also more commonly, especially when you're developing pipeline and not specifically sharing them yet, you would simply run your local main.nf, which by convention is the name for the main Nextflow script, or you can call it whatever you like in most cases. So speaking of integration with Git and sharing pipelines, and this important aspect of reproducibility here, what you can do, you can run a specific revision of a pipeline. So you can Nextflow run hello with revision pointing to a commit hash, to a specific branch perhaps, or a tagged version. So if you've tagged your code, your commit with a specific tag, like here the version 1.1, Nextflow will pull or check out the correct revision and execute that rather than just the head of master as it would normally. So as we can see, the version 1.1 is being executed here in this case. So some basics on how we run Nextflow on the command line. As we said already, Nextflow run main NF. That's pretty typical. And the main thing to remember here, we've got two kinds of parameters or options to pass with those commands. First, we have Nextflow parameters. Like, for example, we want to run our Nextflow pipeline with Docker. So you might do with Docker. Importantly, it's prefixed with a single dash. Similarly with resume. So I already mentioned briefly the caching, and that you don't have to rerun the whole pipeline, but only chunks, only parts that rely on modified inputs. So dash resume is the option that ensures that. And common mistake is to double dash it and to be surprised that a whole large pipeline is executed. So I think everyone makes that mistake at least once. Double dash parameters are for your pipeline options parameters. So if you say dash dash input and a file name here, then this file name is available to your pipeline script under this variable. So you've got the parameters, essentially a map, where the key is the name of the parameter you used here, and the argument, the value passed, is in this case is the file name. There are some parameters you can set via environmental variables, and relevant to this webinar is setting the specific version of Nextflow before running it. So for consistency with the results presented in this webinar, you might prefix your Nextflow run command with this by set the Nextflow version to the specific one. So in the webinar, we'll use and the associated tutorial, we re-implement a workflow that Nathan Watson-Haig developed for his Embo ABR SnakeMay webinar, which also may help you with comparing how things can be done in Nextflow compared to SnakeMake. Mind you that the way it is implemented is to keep the implementation as simple as possible, so not necessarily optimal, but rather as readable as possible. So I think that bearing this in mind, we'll look into the details in a moment. As for what's happening in the pipeline, I think we basically wanted to capture a set of common operations that might be done to capture a fragment of a pipeline that's reasonably realistic, while being also manageable for someone to use as a learning aid. So let's have a look at the pipeline. So we've got our main Nextflow script. As as before, we have the Nextflow shebang line, which is optional, as I mentioned. There are a few steps with comments on making the thing run and initiate, where to get the data from, and so on. We generate a few channels based on the inputs defined in a separate file. We'll get to that in a moment. But just to have a sort of a scour around the script, we have our processes as shown before. Generally, you rely on Nextflow for placing the data and the script in those in separate directories. So it's generally not good practice to try and force the files in a specific structure. Now, we make an exception here with this directive store there to make sure that the input files we download are stored outside the Nextflow structure normally used. This is just to prevent re-downloading data sets, and also to keep them later as well in case our work directory gets deleted. So I guess in your own time you can go through the details of the individual processes that we have here. But I think the common themes that you will see everywhere, you will have this main sections for each process. You have the place to set the directives. So you could, for example, set that this particular process, which involves compressing some files, can use 2 CPUs or 2 CPU cores, and we also use tags so that our terminal output is a bit more informative about what is actually being processed by individual task. You also have the input and the output blocks, which will read from channels and output files and values into other channels. And you also generally always have a script block that can be delimited by this triple quotation mark, where your bash code is embedded. Now, mind you, this can be any scripting language that you want to use. So just by including a Python shebang line, for example, this could be a Python script. It doesn't have to be bash, it's just the default. So without a shebang line, it is assumed to be bash. Another thing to note is that although this is bash, there are different ways of doing that. But in this generic example, the dollar variable prefixed with a dollar, this is not a bash variable. This is an Nextflow variable that we get. So our file name of the reference picked up from the references channel is what will be embedded in this bash script before it's passed to bash. Similarly, the number of the CPUs or threads we want to use will be embedded in the script before this is passed to bash. So there are ways of separating and escaping variable names to make sure that you use the right one. I guess this is a common cause of problems early on, but there are also different ways of defining the script block which help with that, especially if you would have to have a lot of those. I think we'll move on to the next slide. As I said, I tried to document the the main file here in some detail, so you can follow the steps in there. So what happens if we run it? We run it with Docker, sorry. So the idea is that we could make the software available in different ways, but in this case, we're relying on all the required software being available in a Docker container. We'll get to how this is defined. But what happens is our pipeline is executed. As I mentioned, the store there process, because I've previously already downloaded the files in an earlier run, those two steps, those two tasks are skipped. Our reference is already there, and the reads for one specific accession that we're running it for this time is already there. So these two are skipped. Everything else is submitted and executed. So the various steps are executed. Now, what happens under the hood is that you'll see that a number of directories is created. These hashes may not be too human friendly in terms of readability, but this is where the files, script files, the input files, and the output files go for each of the tasks. Now, if we look a bit closer at some of those, we'll see that the input files for a given process and the output files, and also a lot of hidden script files, which contain, so for example, this one will contain the bash snippet that was generated by Nextflow. So this goes back to this idea of isolation of individual processes and tasks, essentially, so that everything is executed within a directory like that. And the channel, let's say the sample data or data chunk traveling through channels manifests itself here as by default a symlink. So this task, whatever it was, had an input defined that included this FASTQ file, and there is a symlink to the actual downloaded reads and the symlink was basically the staging of the inputs in the work directory. So this initial execution that I showed you was just for the one accession. Now what we can do, by default, this pipeline does only one accession. We can also do two, for example. And if we do it with the flag resume, you can see that the jobs, the tasks for the first accession have already been processed. So these are cached, so essentially skipped in this case. For the next one, which is called Olsen, the other accession, jobs are submitted. And again, you can see the prefixes of the directory names that you can use to locate your commands and data in case anything goes wrong and you need to debug. I would just like to re-emphasize that you use the resume here to make sure that the whole thing doesn't get entirely rerun. Now, configuration files. The main configuration file is assumed to be nextflow.config. It sits next to your main.nf, your main Nextflow script. You can also have some global settings in your home directory hidden Nextflow config file, but you can also have additional config files included in your main config file. You can extend or override the config settings at runtime as well. So there are different scopes in config which allow you to separately define, let's say, parameters for the pipeline, like inputs or settings for tools being used. You can set attributes for the processes, so things like how many CPUs they use, and you've got scopes like Docker where you can set up Docker-related settings. You finally have config profiles, which are very useful when you want your pipeline to be portable, or if you want to be able to run the same pipeline either with Docker or Singularity. The easiest way of doing that, or probably the most robust way of doing that, is to define separate profiles for the two. So speaking of that and the separation of workflow logic from compute, so as I mentioned, as you could see in the main script for our webinar, you could see there are those this block at the top of your process definition where you have directives. That's where you normally can set quite a few things, like that your executor is not local but maybe a Slurm cluster, or that you want to use a specific SumTools module on that cluster if that's what it's available. But this is something that you might do in development, or maybe if you're really just sticking with one environment and one software system. Now, if you want to be a bit more general, it's probably better to define those as separate profiles. So, for example, in this case, we have a Conda profile, which ensures that the Conda environment is defined and built for that when at execution time. You can have a Docker or a Singularity one as well, similarly, and you can use a combination of the two, because you can have profiles that are, like in this case, you can have a Singularity profile, and you might want to use it alongside a Slurm profile, Slurm profile and a Singularity profile together to run your pipeline on the cluster using Singularity for software environment. So this is how you would then call that. So on a local machine or on a standalone server, you might run our webinar example using the Conda profile, Docker, or Singularity. It gets a bit more complicated, as I mentioned, with running on an HPC. You might use the Slurm profile with Conda, and just make sure also that you load Conda module itself, whatever you define it to be. Similarly, as I mentioned, Slurm, Singularity, and again, we want the Singularity must be available to all of the nodes that will be used, all of the jobs that will be submitted. So this is how you make sure that happens. Now, we also are able to run the same workflow on the cloud. In this case, it's AWS batch system. You could also use a few of the other alternatives. This is probably at the moment with Nextflow the most mature option, but I know that development of Nextflow integration with Google Cloud is improving as well. And there's also an alternative way of using AWS directly using an Ignite-based setup. So speaking of software environment, we already mentioned the different profiles that are specific for software here, like Conda, Docker, Singularity. There are different ways of doing that. So you might already have all the software installed on your system and not worry about that. But more commonly, you would define general environment for the whole pipeline, or maybe environment for parts or a specific process within your pipeline, or you can mix it. Perhaps you have a default environment for generic processes using standard Linux tools, and then you have something very specific for a process that uses some obscure tools that might not be normally available. So for the workflow presented here, we have a Conda environment captured in a Docker container and a Singularity container built from that as well. So Conda is great, but it can be slow. Defining the dependencies with specific version is good, not just for reproducibility, but apparently also for speed. To be fair, I don't use Conda all that much, but it can be really great here as a means of building a container. But if you do like to use Conda, this is how you would define that in your Nextflow config. Essentially, it's really all there is to it, if everything goes well. You basically define where your Conda YAML file sits, and you define your Conda environment as you normally would. Now, as I said, we use that to build a Docker container. So we have an automated build set up on Docker Hub. So when we commit any changes to our Docker file, we can trigger a build on Docker Hub, and based on this Conda definition, a Docker container image is built, and then in Nextflow config, we defined what the container is. So here again, for the webinar, we defined just the one container for the whole pipeline, but you could do that, or you could specifically set separate containers for different processes. Or as I mentioned earlier, you could mix the two, have a general one like this, and then have a different one for some specific process. So there are some of the other options you would set with Docker. There are some ownership issues that Nextflow solves in most cases. Another upside of having a Docker set up is that this is the default setup for AWS Batch. So we also have an AWS Batch profile, which relies on the same Docker container. Similarly with Singularity, you could define it from scratch, as you could define the Docker container from scratch. Need not use Conda in the same way you don't have to use Docker to build Singularity. But this is, if you want to support both, that might be an easy way of doing that. In our case, our Singularity recipe is rather minimal. It's simply, we're telling it to use Docker and build the Singularity container from that. Now, you could also skip that step and get Singularity could pull the Docker image and build the Singularity container on the fly, or maybe not on the fly because this will be cached and you won't be doing that again probably, but Singularity can do it directly at runtime. And again, we have a profile defined in Nextflow config where Singularity can pull the container from Singularity Hub. And if you just stick to Docker, you could just put in the Docker repository here as well, with some downsides for reproducibility perhaps, because you have to rebuild, the container will be rebuilt locally only. Okay, pipeline outputs. As mentioned earlier, you've got those work directories, which are pretty hard to navigate, not being particularly readable with all the hashes. There is a publish dir directive, which tells Nextflow to capture specific outputs and put them somewhere where a human can find them easily. So in the case of our pipeline, you could, in a separate config file or in the main config file, you could define that if a process is called multi-CSIRO, you want to put the output files into this directory, and the mode is about whether it's a symlink, copy, or moving of the file from the work directory into that final published directory. So you could do something similar for other names. You can be a bit more generic. You can have a label, call multiple processes, give multiple processes a label stats, for example, or figures, and anything with that label, any outputs declared there will be output to a directory you specify in this block. So when we look at the results of our pipeline, we see that one of the published directories is here, a BAM file for the single accession. Those are the store dirs that I mentioned. So when we want to keep the input files captured and not part of the main Nextflow directory structure, that has some risks. So although it makes that's a good way of making sure that things will not be re-downloaded even if you delete the work directory. It also means that if any of those files has changed or was corrupted, the execution of those tasks will be skipped anyway because there is a file called like that. So there aren't any extra checks for that. So coming back to the published dir directive, here are the other two examples where the QC, multi-QC results have been stored in those specific directories. So if we want to rerun our pipeline on the cloud, this is how it could look like. This is speeded up slightly because there would normally be some lag in how the tasks are processed, especially on the initial stages where data are pulled from remote sources. In this case, specifically for this pipeline, we use the take all to do all the samples, all the accessions. So in this case, there were a few that were done before, and everything else is submitted for the first time. So the previous one has been cached and are not rerun. The new ones are, and then any downstream processes which rely on like multi-QC, which involve generating plots from all the samples, are always rerun essentially if there is even one new accession added, and that's the intention. Okay, a few other things that Nextflow provides sort of for free out of the box is the introspection. So looking at how the pipeline was executed. For example, you get very nice execution reports like this one. So this is the execution report for this AWS batch run. So you've got the exact command used. You know that many tasks have succeeded. That many were run before and cached, so not rerun. You've got how many CPU hours were used in total, locations, and so on. Now you get a bit more. You've got CPU usage by task. memory usage, job duration, and also specific information about individual tasks, which can be pretty useful if something's amiss. In addition, you also get timelines. The timeline for the AWS batch run is not that interesting because everything happened a bit too quickly. When we have a run on a local machine with just on a VM with just 2 CPU cores, you can see that most tasks on this timeline are happening in sort of in pairs. They are submitted, processed, as I said, usually in pairs. There's not much waiting time in general, but this can be pretty useful and pretty impressive, especially in like HPC execution environment, where you would see a lot of tasks executed simultaneously, independently of each other. Now, for Nextflow resources, obviously you'd go to Nextflow.io, so the main Nextflow website, which can redirect you to the documentation as well. Nextflow patterns, the next one here that's really useful for more advanced stuff. So when you hit some wall when developing with Nextflow, there might be an example of how to deal with some less common, maybe not that less common, not quite common in fact, but slightly more advanced solutions. Nextflow Gitter Channel is really useful. You can get some knowledgeable advice from users and also from developers of Nextflow on how to deal with different issues you might face. Also a list of different Nextflow pipelines, and finally NF Core, which is a really great initiative where a lot of attention is put to reducing effort duplication. So when you then want to embark on implementing some pipeline, I would suggest have a look there first, whether there isn't something really similar implemented already, or perhaps you want to join them and add some new pipeline, which would follow some of their principles that they defined for pipelines, because there's a great way of getting to your results much more quickly if it so happens that so probably don't start a new RNA-seq alignment pipeline. Use or adapt the one that's there, which would benefit to you and the community. Finally, I would like to acknowledge Nextflow and the development team for creating this fantastic tool. The community on Gitter, which helped me a lot and always very helpful with Nextflow issues. Thanks to Nathan Watson-Haig for preparing the original pipeline on which this one is based. And finally, last but not least, my colleagues and superiors at CSIRO, Alex Van de Gent Taylor, for supporting my efforts in my work on reproducibility in computational science, and our HPC support and others who made this all possible. Thank you.
Okay, well, thanks, Brad, very much for such a wonderful overview of Nextflow. It was some really great practical tips there for people too, so thanks again for the info. We've had some great questions come through. We are running short of time and they're quite technical in nature, but Rud has confirmed that he's happy to respond in writing to those questions, and we'll post the Q&A with the recording afterwards to make them accessible to everybody. So thanks again very much, Brad.
Thank you, Christina.
And thank you everyone for joining us for today's webinar. If you ever have any suggestions for future webinar topics or suggestions for speakers, please feel free to let us know and email us at webinars@mblabr.org.au. And you can visit our website at any time to access the registration links as they become available for our next webinars. The next one will be from Natalie Thorne, who's the Melbourne Genomics Lead Specialist Clinical Genomics. And she's going to speak with us about bioinformatics in a shared clinical system for genomics with reference to Genevic. So thanks again for making the time today to attend the webinar. As you know, it's been recorded and the resources will become available soon, and those that have registered will be emailed to let you know when it happens. So finally, NCRIS would like to acknowledge the funding from Bioplatforms Australia and the University of Melbourne that we receive, and the ARDC would like to acknowledge funding from NCRIS. So thanks again for attending today, and goodbye.